Okay, hello everyone. In a new video, so we have reached part 9 of chapter 7, which is chapter of Newton's second law, and this for grade 11 students. Now, previously we have reached exercise number 15, and we have claimed that the acceleration of the system will be given by this expression. Now let me recall how did we obtain this expression. So notice that m3 and m1, okay, for the numerator the acceleration will be given by the numerator the total masses involved in the system, they are given by m1, m2 and m3, whereas for the this is for the denominator. For the numerator it's also a combination of masses with plus or minus. Now plus sign if they are with the direction of the weight, which is the gravity. So m1 and m3 will be plus sign, so this is plus and plus. As for m1, it will include a sign of the inclination, which is sine alpha. Now as for m3, it is completely opposing the action of gravity, so it's given by minus m3. Now we will apply Newton's second law separately on each body in order to determine whether this expression is correct or wrong, okay? Let me keep it here. So is that true? Then now let's proceed. 3 blocks S1, S2 and S3 of respective masses M1 is equal to 600 grams, which is equivalent to 0.6 kilograms. M2 is given by 0.2 kilograms, and M3 is equal to 0.3 kilograms. Are connected by means of two massless and extensible cords, which means that tensions are being transmitted equally at the end of these cords. The trap over two light pulleys as shown in the adjacent figure, so the mass of the pulleys are neglected. Okay, the inclined plane makes an angle alpha is equal to 30 degrees with the horizontal. The force of friction F between S1 and the inclined plane is supposed to be constant with magnitude F is equal to 0.9 newtons, and take G is equal to 10 meters per second square. Now here I have noticed that friction is being involved in the problem. So now this expression is no longer true. There will be a modification. But how we will compare the one that we will determine with this one if they are correct or no? Simply if we set F is equal to 0, this must be reduced to this expression, okay? So it must be reduced to this expression. Now, okay, we have that F is equal to 0.9 newtons and take G is equal to 10 meters per second square, which means that this experiment is being performed on the surface of the Earth. So now I repeat, when we will determine the acceleration here in this case, the expression will be different than this because there is a force of friction. So we expect that here we will have minus F, not here. We will have, I think, somewhere here that involves its minus F. However, when we set the value of F is 0, the expression that we will obtain must be equal to this one, okay? Now number 1, they are telling me name and represent the external forces acting on each block. Let's start by the block S3. So let me redraw the figure here. So let me draw each block separately. So suppose this is S3. Now we need to choose a reference system because we expect that S3 will be going upward. Then let's take a fixed direction of motion. So suppose the system is moving in this direction. So this is the positive X direction, say for example, or Y, it doesn't matter. We have the weight which is acting vertically downward like this. And we have the tension T3 along the cord which is acting vertically upward like this. So this is the weight T3 and this is the weight W3. Okay, so we have the weight W3, we have the tension T3 for S3. Now notice that for each solid we can choose a different reference system, but the thing is that the direction of motion must be fixed for all of these three, and always the positive direction of the axis must be taken in the same direction of motion. Now as for the solid S1, so this is the inclined plane like this. Then this is the angle alpha. This is the weight which is acting vertically downward like this. Okay. Now we have, okay, what else do we have? We have the tensions. So let me say, this is the string 1 for example, and this is the string 2. Now if this is T3, so let's say that this is T prime 3 in order later to equate between them. So this is 3 and this is 2. Let's ignore 1 because 1 is common for 3 and 2. Now, okay, let me choose the axis. So we are supposing that it's moving downward. So let me say that along the plane. So let me say that this is the positive direction of x. This is W1. We have the normal reaction like this. Okay. We have the tension which is acting away from the object. This is the tension, we say T2. And we have the tension T3. But recall that also we have the force of friction which is given by F is equal to 0.9 newtons. Since this is supposed to be falling down, then the force of friction is opposing the direction of motion, which is like this along the inclined plane. Now other than that we don't have anything. Now as for the solid S2, let me here mention the forces. We have the weight, so this is for force for S2. We have the weight, so for S1 we have the weight W1, we have the tension T2, we have the tension T3, we have the normal N, and we have the friction F. Now as for the solid S2, so we have the tension which is vertically upward like this. We have the weight which is vertically downward like this. And we'll choose the direction of motion, the positive y or x direction along the direction of motion, exactly opposite to the one above. And in this case this will be the positive direction of the x-axis. This is the weight W3, this is the tension T3. Okay, so what are the forces acting for the solid S3? We have the weight W3 and we have the tension T3. Okay, and notice that the system is in the dynamic mode, so we cannot apply the condition of equilibrium, although we have two forces. Now in number 2 they are telling me apply Newton's second law on each block, so this is important. So here no need to consider a system, but rather to apply Newton's second law on each block. Okay. So now let's start by applying on the blocks S3 and S2 since they involve the least forces, number of forces. Then apply. Okay, first let's determine the projection of the forces. So now we are applying it for the solid for S3. Sorry, this is S2. Let's start by the solid S3. So for the weight W3, we have W3x and W3y. For T3, we have T3x and T3y. So in this case, T3 is with the direction of motion along the x-axis, so this is plus T3, this is 0, and simply this will be minus W3 and 0 here if you check the figure correctly, okay? And now we are ready to apply a Newton's second law. So apply, recall that this is not a condition of equilibrium because we have dynamics. Apply Newton's second law for S3. So we have that sum of forces is equal to the mass M3 multiplied by A, which is W3 plus T3 is equal to M3A. Now projection along the axis of motion, which is the x-axis. We have the W3x plus T3x is equal to M3AX. So here if we place 3, then we will equate between the different accelerations. So this is A3x. W3x is simply given by minus W3 plus T3 is equal to M3AX. So in this case, T3 is given by M3AX plus AX. Sorry, M3AX plus W3. This is A3. Now here A3 is given by square root of A3x squared plus A3y squared, and this is simply 0. A3y is equal to 0, no motion along the y-axis. So simply A3 is equal to, this will give us either plus or minus sign AX, so this will be plus A3x. Okay, so in this case, T3 is equal to M3AX plus W3. So this is the first equation. Notice that in order to determine the acceleration, we need to equate between the tensions. So we are done for the solid S2. Now let's move, with the solid S3. Now let's move to S2. Now for S2, so what are the forces acting on S2? We have W2 and we have T2. So W2x, W2y, T2x, T2y. So W2x is in the same direction, which is plus W2, and this is 0, minus T2, and this is 0. Now let's say apply Newton's second law for S2. We have that sum of forces is equal to M2A, which is W2 plus T2 is equal to M2A. We cannot apply the condition of equilibrium because this is the case of dynamics. And here let me say projection along the x-axis, which is the positive direction. So simply we drop down the vector quantity. Each vector quantity will carry the label x, and this is 2, 2, m2 a2x, w2x is plus w2 minus t2 is equal to m2 a2x. a2 is equal to square root of a2x square plus a2y square. So this is 0 because no motion along the y-axis. a2y is equal to 0, no motion along the y-axis. So simply a2 is equal to plus a2x, y plus, because in the same positive direction of the x-axis. And in this case, w2 minus m2 a2 is equal to t2 if we rearrange the equations. So w2, t2 is given by w2 minus m2 a, and here simply no need to write the x component because we have equated it with the magnitude a 3. So notice that here all of the indices are 3 and here all of the indices are 2. Okay, so now w2 minus, okay, we need to apply Newton's second law for the solid S1, which is the connection between S2 and S3. Then for S1 we have several forces acting on S1. Let's start by the tension T2. And first let me determine the angles. So the positive y direction is like this. Right? So if this angle is alpha, so this angle is pi by 2 minus alpha, which is also this angle because this line is parallel to this line. And this angle is alpha. So now T2x is plus T2. Now T2y is 0. T2 is pointing in the positive direction of the x-axis. Now as for the force T3 x is equal to minus T3 and T3y is equal to 0. Now in this case W1x is equal, it's pointing in the positive direction of the x-axis, so it's plus W1 cosine pi by 2 minus alpha, which is W1 sine alpha. As for W1y, it's equal to minus W1 cosine alpha because it's pointing in the negative direction. Now as for the force of friction, which is F, so F1x is equal to minus F and F1y is equal to 0. As for the normal N, so Nx is equal to plus N and Ny is equal to what? Sorry, Nx is equal to 0 and Ny is equal to plus N. And now we are ready to apply Newton's second law. For S1, we have that sum of forces is equal to M1A1, sorry. We have the W1 plus T2 plus T3 plus W1 plus F plus N is equal to M1A1 Okay, now let's do the start by the projection along the x-axis. So we drop down the vector quantities, and each vector quantity will carry the label x. This is simply 0. Now w1x is given by w1 sine alpha plus t2x is given by t2 minus t3 minus f, okay, plus, okay, which is equal to m1 a1x. Notice that a1 is equal to square root of a1x square plus a1y square. No motion along the y-axis, so it's simply plus or minus a1x, and we'll take the positive because in the positive direction of motion. So now w sine alpha plus t2 minus t3 minus f is equal to m1 a1x. And here let me also say that this is t prime, this is t prime, this is t prime, t prime. They are different in the tensions, but they are equal. Later we will specify that it's due to an extensible string. Okay. So now the new equation that we have is this, which is given by w1 sine alpha plus t2 prime minus t prime 3 minus f is equal to m1 a1. Now let me drag these equations that we have. Okay, t3 is equal to m3 a3 minus, let me see, plus w3, and the other equation is given by t2 is equal to w2 minus m2 a2, and we are interested in determining the acceleration of the system. So now we can pose the following constraints that are given by that a1 is equal to a2 is equal to a3, and t2 is equal to t2 prime, and t3 is equal to t3 prime, and this is given by all chords are inextensible. So now we need to determine the acceleration. The acceleration is simply determined by replacing this here, because they are equal, and this here, and we are left with one equation and one unknown, which is given by the acceleration a. So w1 sine alpha plus w2 minus m2 a2 minus, we open the brackets, m3 a3 plus w3 minus f, which is equal to m1 a1, and all of these a's are equal. So w1 sine alpha plus w2 minus m2a minus m3a minus w3 minus f is equal to m1a, and we are interested in determining the value of a. So rearranging for the equation, we say that a is equal to, we have the numerator, so bringing f, okay, wait, this is a bit complicated. We have that a multiplied by m1 plus m2 plus m3, which is equal to plus f, sorry, minus f, okay, and plus w1 sine alpha plus w2 minus w3. So in this case, the expression of the acceleration is given by w1 sine alpha plus W2 minus W3 divided by M1 plus M2 plus M3 minus 1 over M1 plus M2 plus M3 multiplied by F. Okay, so let me do them carefully again if you want. So now dividing both sides by, so we drag this to here, and we flip the equation, we will obtain this one. Then we divide by M1 plus M2 plus M3 on both sides. So this is given by A, which is equal to, now we drag this fraction to the left, so it's given by W1 sine alpha plus W2 minus W3 divided by M1 plus M2 plus M3 minus this fraction. I will write it in the following form: M1 plus M2 plus M3 multiplied by F. Okay, so now W carrying the index 1, 2, 3 can be written as M1G sine alpha plus M2G minus M3G divided by M1 plus M2 plus M3 minus 1 divided by M1 plus M2 plus M3 multiplied by F. Now taking here G as a common factor is given by M1 sine alpha plus M2 minus M3 divided by M1 plus M2 plus M3 multiplied by G minus 1 over M1 plus M2 plus M3 multiplied by the force of friction. Okay, now we started with the following. Okay, I cannot copy it again. Okay, we started with we claimed that the acceleration will be given by A is equal to M1 sine alpha plus M2 minus M3 divided by the total mass of the system multiplied by the value of G, right? Then later on I said that this expression will be wrong because it includes F, so the factor of F appeared here. But simply if we set F to 0, so all of this will be 0, then the acceleration will be reduced by this, which means that our answer is correct. Now we need to determine, we need to give a numerical value. So let me say that the value of F is given by 0.9 in newtons. The value of alpha is given by 30 degrees. The value of M1 is given by what? 0.6. The value of M2 is equal to 0.2 kilograms. And the value of M3 is given by 0.3 kilograms. Now let's plug in the values. A is equal to 0.6, and here we must be very careful. We don't want to make any mistake. Plus M2, which is 0.2, minus 0.3 divided by the total mass, which is given by 0.6, plus 0.2 plus 0.3, G, which is 10, minus 1 over 0.6 plus 0.2 plus 0.3 multiplied by the force F, which is given by 0.9. Now let me plug these complicated fractions on the calculator to obtain the value, the numerical value of A. Okay. Then the acceleration simply is given by 1 meter per second square. Okay. Now after that they are telling me to determine, I think, the value of the tensions. Now if you go back and we need to determine the, deduce the nature of motion of each block. So simply the nature of motion of each block is UVRM Why? Because the trajectory is linear, is a straight line, and the acceleration is constant. Okay, why the trajectory is straight line? Because this is moving up, this is moving a straight line with an inclination, and this is moving down with a straight line. Now they are telling me to deduce the value of the tensions. The value of the tensions can be deduced by referring to these equations. So T3, which is equal to also to T prime 3, T3 is given by M3A3 plus W3 which is given by, what's the value of M3? 0.3 multiplied by 1 plus 0.3 multiplied by 10, which is 0.3 multiplied by 11. Okay. So it's given by 3.3 newtons. We have that T2 is equal to T prime 2, then T2 is equal to W2 minus M2A2, which is equal to M2G minus M2A. You can take M2 as a common factor or simply plug in. So now M2, which is 0.2 multiplied by 10 minus 0.2 multiplied by 1, which is 0.2 times 0.9, which is given by 1.80 newtons. And here we expect that the value of the tensions are positive, independent whether they are acting in the positive or negative direction, but these are the magnitudes, and we have taken into consideration the different signs regarding the tensions, the frictions, and the weight. So T3 is simply given by 3.3 newtons, and T2 is equal to 1.80 newtons. So that's it for me in this video, guys. In the next part, we'll start explaining the projectile motion.